This is a bonus lesson to wrap up the first part on air chemistry. When I taught this class face to face, there was so much going on, and this is not my area of expertise. It's becoming more of an area of expertise. I was having trouble just keeping track of everything. So what I have for you here is sort of a summary, and I'll try to do this in two different whiteboards. What are some of the main things we want to think about when it comes to the stratosphere and the troposphere? And we'll do that, we'll do it the way the book organized. So we'll come from about 50 kilometers up into the atmosphere down to about 15. You might recall that's the stratosphere. And then what we call ground level is where it's called the troposphere. Now I'm not covering everything here. I'm not going through all the chemistry and the math that we did the last two lessons, but I thought that for me this was a useful summary to kind of get the big picture of stratospheric chemistry and tropospheric chemistry. So these are just bonus. I don't know if you'll find them very useful, but it was useful to me to kind of get my head around the big picture because I was kind of losing track amidst all the different little things. Okay, so this is really optional. I don't think I'm going to have you respond to this in any way, but it's also a good way of taking stock of everything you've done so far. Okay, so forgive me, I kind of have a cutesy little picture to start. So let's, this is just a diagram, my own diagram, combining chemistry. So let's talk about the stratosphere. And I'm going to go upper stratosphere, lower stratosphere. I'm not very good at scientific graphics. So we're going from about 15 kilometers at the low point up to about 50 kilometers, so 15 at the low, 15 at the high, and forgive me, here's my little happy sun. So we pay attention to the sun, and what's coming out of here is UV vis. We'll talk a little bit more about nuclear chemistry and what's going on in there in addition to other things about nuclear chemistry. And what we're concerned about in stratospheric chemistry from chapter 1 is ozone. That's what we're concerned about. And I just did this, again, I like this because it helped me stay organized. So we have to produce ozone. Ozone does not exist naturally in the stratosphere or the atmosphere anywhere, so it has to be produced somehow. So how do we produce ozone? This is just a summary of what we did before. Well, it starts with what is present and uses high energy ultraviolet to produce atomic oxygen, and that's an endothermic process. Then those two oxygen atoms react with two more diatomic oxygens to produce two ozones, and I'm doing this so that it balances properly. And that's exothermic. And you have the chemical equation that all books show. 3 oxygens become 2 ozones. But it's more complicated than that. So all of this is important to remember. And I had a couple of footnotes. So footnote 1. Where should I put those? Put those down here. So footnote 1. This is an important reaction. That temperature inversion that we talked about in the stratosphere, that's very important, that you get the massive change in temperature. It's this exothermic reaction that causes the temperature inversion. That's footnote number 1. Okay? It's production of ozone. And then the destruction of ozone. Oh yes, in the stratosphere contains about 90% of all atmospheric ozone. That's important. You don't want a lot of ozone on the ground level, tropospheric level. You want most of it up there because of what we're doing here. The destruction happens in two flavors. Non-catalytic, so non-cat, and what's happening there. So non-catalytic means it's just kind of, well, doesn't need a catalyst. It doesn't need quite as much energy. So ultraviolet B will work, ultraviolet C is better, and you get excited diatomic oxygen and excited atomic oxygen. And then another ozone reacts with the excited oxygen to make two O2s. And that's a way of destroying it. Now, this is a cycle that's non-catalytic. Don't think I have any notes to add there. Cool. Then you have catalytic destruction, so production, destruction of ozone. Well, what does that mean? Things we put into the atmosphere. So this just happens. Catalytic, non-catalytic just happens. Catalytic is something we end up producing and putting into the atmosphere. And remember, we just use placeholders. So we just call a catalyst generic X. And then if it's more than one catalyst, we just call it X prime. So it's, oh, sorry, that one is not that one. So it's just one catalyst and another catalyst. So it's prime, not one. And then we had two mechanisms. We had mechanism 1, which involves atomic oxygen, and then we have mechanism 2. So mechanism 1, your catalyst reacts with ozone. It pulls off one of the oxygens and makes, I'm not going through all the radicals and all that good stuff right now, just the big picture. And then that intermediate species comes down, reacts with atomic oxygen that's produced through non-catalytic procedures, and you generate X back, which is why it's a catalyst, and then oxygen. So overall with this reaction, let me double check that. Yep, so in this case, it's ozone reacting with atomic oxygen to make 2O2. Again, that simplifies the picture. The catalyst is necessary to make that happen. That brings down the activation energy, it accelerates the speed. So that is taking ozone plus atomic oxygen, but it requires the catalyst. That is mechanism 1. Mechanism 2 is really just a variation of the same theme. There's possibly more than one type of catalyst. Okay, so the first reaction is the same. Then if you have more than one thing happening at a time, another catalyst, I don't know why I'm looking at my notes. Then your two intermediates are regenerated. And you get the same, you get what we saw before. 2 ozones produce 3 diatomic oxygens. For me, I just found this helpful to keep the big picture. So you produce ozone, you have 2 mechanisms for destroying ozone. One happens naturally just by virtue of ultraviolet light produced in the sun. The other one is accelerated by the presence of a catalyst that we put up into the atmosphere, one of those catalysts being chlorofluorocarbon CFCs. I found that helpful. So that's a sort of a summary of the ozone chemistry of the stratosphere. And you'll notice we're not talking a whole lot about health effects up here, because the main health effect is, does ultraviolet light get through or not? So if we deplete the ozone, we are having trouble because of that, but that hasn't been a major issue for a while. So we're not talking about a lot of pollutants in the stratosphere. The troposphere, however, and this is going to be impossible for me to do on one slide, but for me it was helpful for the big picture, because I'm not getting into the interface between what's produced and then water systems, either precipitation or just an aquatic system like we're going to do in another part of the course. Okay, so I think I'm just going to keep this as one video. Again, it's not useful to you, and I have to make a slightly different graphic. It's not really a graphic, it's a table. This marker's a little bit hard to erase. So this one, I'm going to basically do a cataloging of pollutants and the hydroxy tropospheric sink to kind of just get a big picture of what's happening. I'm sorry, this marker, I used a different marker here, it's not erasing very well. Okay. Maybe this is an exercise you should be doing rather than me, but I found this helpful for me. I think that was good enough. And let me get that other marker. So now what we talk about, we're talking about the troposphere. So from about 15 kilometers down to ground level. Now here, we're not really worried about the altitude as much, so I'm not going to do that kind of thing. What I want to do, look, see how I want to do this here, is, okay, so in the middle, the troposphere, remember that we have this tropospheric sink that essentially acts as a way to scrub pollutants from this. And there's different ways to do it, but the one we primarily talked about was hydroxyl radicals and the vital role that they play. And how do we get those? Well, we get the hydroxyl radicals from ozone. Now, you're not going to be expected to memorize all of this. So, hydroxyl radicals, they form because of the natural presence of ozone, which is about 10% of the remaining ozone in the atmosphere, so there is some there, not nearly as much, and it will just naturally produce hydroxyl radicals. Now there, it's really important that they are able to remove pollutants. And I think the example I showed you was removal of carbon monoxide, a very, very dangerous pollutant. And how does that work? Well, carbon monoxide reacts with a hydroxyl radical to make the HOCO. We call that equation 1. And then oxygen reacts with the HOCO to produce, well, HOO, I guess, plus CO2. So this is a way of taking carbon monoxide and removing it as carbon dioxide, something that's much, much less reactive. Okay, the rest of this is really just kind of a cataloging. Okay, it's well, let's put these over here. So the troposphere, we have primary pollutants, carbon monoxide, we have the NOx, we have the SOx, we have hydrocarbons like methane. You might recall that natural gas also contains a high amount of dihydrogen sulfide. Then we have ammonia is another common pollutant. And then the giant class of chemicals called volatile organic chemicals. And I think I had a couple of footnotes here. Well, where do these come from? Well, some of these come from combustion and refining of metals and minerals. Let's see, that's going to be carbon monoxide comes from that, nitrogen monoxide there, nitrogen dioxide, sulfur comes there as well. Okay. And then you also recall, this is a footnote, is thermal nitrogen monoxide production. If you take nitrogen and oxygen that just exist in the atmosphere, and under conditions of high temperature, an engine, a power plant, you produce thermal nitrogen monoxide. So that is another way we get that one, not just from combustion, but also from thermal production. That's kind of important. Another source of primary pollutants are volcanoes. OES, that's right. And plant decomposition. So natural, if you will. And where do we get some of these things? Well, we get SO2 from those things. And it's the only one I'm labeling there. And the last one, very important, is from natural gas mining, which of course is going to be here and here. I think that's it. And ammonia can be, I didn't label that one there, but that's primarily going to be from fertilizers. Okay, so those are primary pollutants. And what's the definition there? Those are things that are produced and become pollutants directly in the environment. So, and this is not dependent upon altitude, please don't interpret it this way. So then we have, it's not primary, it's secondary. We've already talked about these. I'm not rewriting all that chemistry. Okay, well, that comes from somewhere. Well, it comes from here, okay? Well, acid is just one example. You can also get nitrogen trioxide and sulfur trioxide. Where does it come from? Well, from those. They become oxidized and go to these. And these are the end of the road. So these are completely oxidized. I should point out that NO3 here is not with the negative charge. That's an ion. Well, the other one we talked about before is another strong acid, sulfuric acid. Well, that comes from SO2. And that's the acid deposition that we spent a lot of time doing the math on. But then you also have particulate matter. Those are secondary pollutants. In particular, sorry, look at that, upon 2.5, then in order to get particulate matter, it comes from a combination of smoke and fog. And then we also have ground level ozone production. Which is something we want to avoid. And you might recall for smog, we did this sort of hand-waving chemical equation. VOCs plus nitrogen monoxide plus oxygen, all in the presence of light. You get ozone and nitric acid. And then a very complicated mixture of organics. That was not a great chemical equation, but that just shows you. Okay, so I think the last thing we're going to put in is where do we get ground level ozone as a summary. So that'll be the last thing on this one. But this is just sort of a nice big picture overview, in my view, of the chemistry of the stratosphere and the troposphere. And wow, this one was kind of complicated. So ground level ozone, I forgot about this. Where do we get it? It's kind of complicated. That's where we have to take into account these hydroxyl radicals, and they react with the HU, one of those intermediates, will react with something like nitrogen monoxide from pollution, and you'll get a hydroxyl radical and NO2. I'll label all this later. Then that NO2 can undergo photolysis. Can you imagine piecing all of this together? But the bottom line is you produce atomic oxygen, which then reacts with diatomic oxygen to produce ozone. And you can add these up if you want to. So this is chemical equation 1, chemical equation 2, chemical equation 3. The final analysis is this is one means of producing ground level ozone in the presence of other pollutants like nitrogen monoxide. And that, folks, concludes part 1 of our course. And we'll see you online.